Okay, so for unit 5, the first basic fact we kind of needed to know were a couple things. The first thing we really looked at were, hey guys, we have this Pythagoras theorem. Because by now you know, we've dealt with a lot of triangles. We have a lot of tools to deal with triangles. I'm pretty confident you guys are fairly good with that. The main concern though is always going to be, well, am I using the right thing? So the focus here is, when do I use it? When you use Pythagoras theorem is when you have two sides and you're trying to find a third side. And more specifically, it is a right triangle. This will not work on non-right triangles. We know our formula for that, right? C squared is equal to A squared plus B squared. A squared plus B squared is equal to C squared, but that's the same thing. You know that C is your hypotenuse, right? And it doesn't matter what A and B are. But C is always your hypotenuse. Now this is to find the hypotenuse, but what if you're trying to find one of the shorter sides? Well, then it's just C squared minus A squared is equal to B squared. Or you can use algebra. Either works. Now, the other thing we looked at was trigonometry. Specifically, we looked at SOHCAHTOA, right? Now, all these mean different things. Just for example, what does tangent mean? I'm not going to write them all, but again, TOA means tangent, T, of theta, which is the angle, is equal to the opposite divided by the adjacent side. And if you remember, your opposite side is always opposite of your angle. The angle you're working with. Your hypotenuse is static. It's always going to be the same. But your opposite side depends on which viewpoint you're looking at it from. So that's what it is. But when do I use this? There's two uses. The first is, we can find an angle if we have two sides. And this is going to use the second function. For example, sine to the power of -1. So you can find an angle with that, because remember, you need to separate these two. And you can't divide by tangent, you can't divide by sine, you can't divide by cosine, because your calculator breaks. So you have to use that second function tool. Now, the second use of this is, you can find a second side of a triangle if you have one angle and one side. If you have two things, you can find a third thing. It's basically what this works. And this is also with right triangles. Mm-hmm. So then we started looking at all triangles. So both of these are just for right triangles, right? Pythagoras and trigonometry only for right triangles so far. But then we started looking at some new tools. We started looking at angle measures, and we started looking at side lengths. Okay, so now if you remember, we have three of each. The first angle measure we have is we can have acute. We can have acute angles, which means that all angles are less than 90 degrees. We can also have a right triangle, which means you have one has exactly 90 degrees. And you can also have an obtuse triangle where one angle is bigger than 90 degrees. So you measure, you label a triangle's angles by whether or not it has a 90 degree or not. And then which way, is it small one or a big one? Then the next one we have is we have different side lengths. So for example, this would be, first one is we have an equilateral triangle. This is where the sides and the angles are all equal to each other. Right? So if one side's, you know what, I am going to do this. So if one side's 5 meters, then that means, you know, every other side's 5 meters, for example. We have an isosceles triangle, which is two sides are the same and two angles are the same. Specifically, the legs, which I'll show you in a second. And then finally, we have a scaling triangle where everything's different. So again, like specifically the isosceles, but it kind of works for equilateral as well, is if you can identify what type of a triangle it is, you can get additional data. If I said, hey, I want to know what all the angles of this triangle are, well, you can't. All three angles add up to 180 degrees, but I only have one. I normally need two to find the missing angle, but no, this is an isosceles triangles. I can see that because I have those little arrows there, these little lines, sorry, to signify that these two sides are the same, which means that these two angles here would be the same because it's an isosceles triangle. The legs are the same. So if that's the case, well, I know there's 180 degrees in a triangle. If I take away the 30, I know I'm left with 150 degrees that I can cut in half and split between these two. So each of those angles then would be 75 degrees, for example. So the first part of this is really looking at triangles. So I'll give you a second just to get caught up. Okay, so I'm going to another page, but if you have room, that's fine. So we looked at, three-sided shapes, triangles, cool, we're good there. But what if we have quadrilaterals, aka four-sided shapes? Now there are 1,000 of these. There are rhombuses, for example. There's trapezoids. There's 1,000 different shapes. That's somewhere in your workbook. I recommend that you review the different shapes. You don't need to have them all memories and all their properties, but it might be very helpful when it comes to solve a question. So everything we know about four-sided shapes really comes from a couple key facts. So we have some key facts here. I want to make this. The first are that four-sided shapes have 360 degrees. The second is that most, and I'm pretty comfortable to say, I think all the shapes you're going to see, so most four-sided shapes, but in the context of this course, all the four-sided shapes you're going to see can be split into two or more triangles, often with a right angle. So whenever you're given a question, a lot of the times you're going to need to break the shape down. So many of the things you're given can be broken down into simpler shapes. And finally, most have a transversal, which I will explain in a second. And or parallel lines. And again, I recommend review the shapes because all shapes have different properties. I won't be going over every single shape here. I'm just telling you now, go to your workbook, spend 5 minutes, look at the shapes. I would not be shocked to see like a rhombus or a trapezoid pop into your final exam. It's probably not going to be a rectangle. It's probably going to be something like that. So what the heck, and I'll use blue for this. What the heck is a transversal? if you remember, if we have, I'll try and draw this straight actually. If I have two parallel straight lines, and then I have something that intersects them, that is my transversal, right? And the second I know that these two lines are parallel, like see these little arrows here, that means it's parallel. I now can generate certain properties from this shape. Now, if you remember, let's use black. I'm gonna make this big. We had 4 letters that we kind of look for when it comes to shapes. And remember what they are?
C, C, and an F.
There's a Z, there's a C, there's an F.
Can't remember the other one.
And the other one is an X.
Oh, X. Yeah.
So, what was the acronym I used? Zebras. I forget what it was. I used an acronym for it. It's 5.2 somewhere in there. But there's a way you can like remember that. Like, anyways, the main point here though is that you use these shapes to find certain properties. For example, for the Z, I know that these two shapes here are the same. These two angles are the same, sorry. For a C, some look at this as a U as well. Both of those need to add up to 180 degrees. For an F, hey, these two angles are the same. And then for an X, these two angles are the same. So we have a bunch of different properties we can kind of generate from this. There is technically another hidden line that we never really talk about, but it is a straight line, which basically means that, hey, a straight line is 180 degrees, right? That's just a kind of like a fact. So it's technically a fifth shape there. But so you can use these shapes to generate properties. And you can remember, you can reverse these too. You can flip them upside down. You can mirror it. It's totally fine. So there's a bunch of different ways that you can use these shapes. Okay, and the last thing for quadrilaterals, but technically all shapes is, so I'm just going to draw a really quick trapezoid here. Or sorry, yeah, I'm gonna so if I have this shape here, again, you could always split this up here into a really nice right triangle. That's a right angle there. So you can always split that up there. But I'm just going to label the sides of this. So we got A, B, C, and D. Oop, D. I'm going to go ahead and set this as point E right here as well. That little thing I've drawn. So again, so one thing that's going to be important to note is you're just going to be able to read what it's asking you. If it's giving you something like, hey, I want to know what angle ADC is, find it. Oh, well, again, you read it, right? So you start at angle A, work your way to D, work your way to C. You're looking for the angle that connects those two. I'll erase my whole shape. There we go. So I'd be looking for this angle right here, right? You're looking for that middle angle, technically, is what that's really asking for. If I give you angle, BEA, for example, Well, it wants to know what this thing is here, which is obviously like a right angle, right? So it's just, you just got to make sure you're able to read that. Sometimes though, they might shorthand this as, hey, what's angle A? So they're not always going to give that to you. So, but if this case is asking for that, so you will need to know the difference between those two things. Well, not sorry, you'll need to know that those two things are the same in a way. But that's quadrilaterals. The final part of this is, what if we have 5 sides? What if we have 6? What if we have 7? What if we have 100 sides? We're dealing with polygons at that point, right? 5 or more. 5 or more sides. Now there are a bunch of shapes. There's a a heptagon, for example. There's a nonagon. Like, what the heck does all that stuff mean? I'm gonna guess you're only gonna need to know 2 of these. An octagon and a hexagon, you're right. For the rest of them, they'll tell you it's a 10-sided shape. They'll give you a diagram that shows it. But the one thing they might refer to by name, not telling you how many sides it is probably either a hexagon, a 6-sided shape, or an octagon, which is an 8-sided shape. I'm a little cramped for space, so here we go. So these are probably going to be the only 2 you're going to need to know by name, at least in terms of 5 or more sides. For 4 sides, they might want you to know what a quadrilateral, what a rhombus is, what a trapezoid is, stuff like that. But those are the big 2 that you need to walk in knowing what they are. So there's really 2 things here. We have interior angles, and we're going to have exterior ones. So let's start with interior angles. So I'm going to draw a really quick hexagon here. So interior angles. So one thing to note is I can always take a shape. I can always take a shape and split it up into triangles. We are going to be assuming, by the way, that all these shapes are regular. That means they all have the same side lengths. So I don't think you're going to see an irregular one. But basically, all I'm doing is I'm drawing just a bunch of triangles here just to kind of show a point. So you can find out the sum of the interior angles with a formula, but I really quickly want to explain what the heck does that mean. In fact, let me just change that to blue. So some of the interior angles. When it's saying that, it wants to know what these blue markers are here that I'm doing. So you're noticing it's going in more than one triangle. So the sum of the interior angles is those blue marks there. And we have a formula for that. It's 180 degrees times n minus 2. And if you remember, n is our sides. So if I want to know, hey, what's the sum of these 6 angles in here? Well, it'd be 180 degrees times 4, because there's 6 sides. 6 minus 2 is 4, 180 degrees times 4, so that gives you 720 degrees. But I have to now split that 720 into all 6 of these sections. So it'd be 720 divided by 6. I don't know what that is, but that's what it would be, right? So that's the sum of my interior angles. Now, sometimes though, they're going to give you a question that's asking for, I'll use green. Hey, what's this angle here? This green angle. Try and pronounce it so it's easier. Oh crap, how do I find that? The green is not a full interior angle, right? It's half of it. So if you're finding this, you'd have to take half of an interior angle because it's perfectly bisected by a triangle. In fact, this one here is a really good example of that. So you just cut your interior angle by half. So those are interior angles. Now you can do more with like these shapes, right? You can always, again, I can even split these triangles up even further. Oh, now I have right angles. Now I can do stuff with it. The whole purpose they're trying to give you here is they're going to give you these shapes and make you combine other elements of stuff you've learned. So now we're going to deal with the last thing of Unit 5, central angles. Take that. So one thing I'm kind of asking here is how many degrees are all 6 of these triangles adding up to? It's a circle, it's 360, right? That's going to be a universal fact. The big circle in the middle is going to always add up to 360. But what if I wanted to just find this one? Well, how could I do that?
360, 6.
Yeah, there's 6. Yeah, I know that there's 6 triangles here. I know it's 360. They're the same ones. Yeah, you're right. 360 divided by the number of sides I have. So to find a central angle, it's just 360 degrees divided by n, which is our number of sides, right? So that's Unit 5. So now we get into the stuff where like technically I didn't teach you, like I had videos of me teaching. So if there's something you're like, I don't remember you teaching, like, or like saying that, let me know. But so now I'm going to go up to Unit 6. I'll just keep that up there. So it's, which was transformations. Transformations. So transformations. So if you remember, this is where it kind of starts with like, let's move shapes. It's really just adjusting shapes is really where it boils down to. And the first thing we kind of started with, what happens if we move it? Specifically, we can do a translation, which is moving it. I'll show you like a picture of this in a second, but it's moving it left and or right or up and down. We could do a reflection, which is creating a mirror image. So think about if you put a mirror like in the middle of your object, what would it look like? So, you know, if I give you something like this, and let's say I say, hey, I've made a triangle here. Sure. And let's just say that, hey, this is a 2 on the x-axis, right? This is 1, this is 0. I'll say this is -1. This is -2. Let's say this is 3. Let's say this is 4. So does it make sense that, hey, this point here is on the 4 on the x-axis. These points here are on the 2 on the x-axis. If I say, hey, I want you to reflect it on x equals x equals 0. That's my reflection point, my line. So maybe you're given a question like this. Well, how would you do that? Well, I would see how much distance is each point is away from our reflection line, which in this case just so happens to be this one here. I can see that, oh, these 2 points are 2 away. So I would draw those 2 away. This point here is 1, 2, 3, it's 4 away. So I would go, imagine it's that and that. I would go a total of 4 away. And then I connect my dots, I draw my shape. And I can see that I've now reflected it. So you created a mirror image, and it's usually going to tell you a reflection point, a reflection line along a line. And the last one, which is usually the most complicated for people, is a rotation. What if I rotate this object? Mm-hmm.
It will. Depending on, so. You all, is it clockworks or counterclockworks or is it clockworks?
Good question. So I was just about to go into that. So rotation is the most difficult because there's some stuff you have to memorize. Is really what it boils down to. So rotation, that doesn't seem that hard to like, what is a rotation? You're moving a shape around. You're like, we know what it's like to rotate an object. Specifically, we're moving a shape around a fixed. Actually, I'm going to do this. Moving a shape around a fixed point. So one of the facts we need to know, and I will demonstrate this in a second, is every 90 degrees clockwise, change X and Y. You change the X, Y coordinates and you adjust the side. So there's a lot to break down there. So I will break that down in just a second once you get caught up. So, okay, so I'm going to start out with how do we rotate? I want to use red for this. So, right, so we here's my coordinate plane, right? all four quadrants. This is quadrant 1, this is 2, this is quadrant 3, and quadrant 4. I know that's weird. You go around, you name the coordinates in a counterclockwise, right? You name it in a counterclockwise. But when you rotate an object, they're either going to tell you clockwise or counterclockwise. If they don't say anything, you would move it from like quadrant, you move it this way, for example. So they'll usually tell you if it's going to be clockwise or counterclockwise, or they'll just tell you degrees. If they say, hey, 90 degrees, you're moving it to you're moving it one whole quadrant. In fact, they're only going to tell you by 90 degrees. They're going to tell you 90, 180, or 270. So you could assume that they will be clockwise. So that's how you rotate it. Now the other thing is, every 90 degrees, how do you change your signs? Every 90 degrees, your X and Y will turn into a negative Y and X. You will rotate those every single time. You will swap them around every single time. So if I'm saying, hey, I want you to rotate this image up here, I'll draw an arrow to it. I want you to take this image. I want you to rotate it 90 degrees. Well, it's going to go into this quadrant here then now, right? It's going to go into quadrant 4. So I'm going to swap my X and my Y, and I'm going to change the sign. So now my 2, 2, well, that's simple. That's 2, 2 turns to 2, 2. And then I apply that negative sign, it's negative 2 and 2. This 2 and 4, however, as I rotate that, that's going to turn into, first off, 4 and 2, but I apply that negative sign. This 3 and 4 is going to turn into 4 and 3, but then I apply that negative sign. So now I have my new coordinates. Now I'm able to do it. I recommend do this approach. Don't try and eyeball it. It is so much easier to make a mistake if you're trying to like, well, I think this point goes over here. So I'm going to quickly just 1, 2, 3, 4. So 2, negative 2, there's 1 point. Negative 4 and 2, there's another one. Negative 4 and 3. Not very accurate because I've kind of messed my diagram up here, but it would rotate into something like that. So rotation's the hardest one for sure. That's the one most people struggle with. So you have to remember like how you rotate. You have to remember what you do with your signs. Not very fun. Oh, oops, sorry. Give me 1 second. I just want to find one thing. Oh, I'm on the wrong unit. Sorry. Sorry, this y will get the negative sign. So I actually goofed up here a little bit. So this will be 2 and -2 still. This would be 4 and -2. And this would be 4 and -3. So I goofed up there. Sorry. Does that make sense? So does that make sense? So I made a little mistake there. So that negative sign gets applied to your former, to what the former y value position was. And you do that for every 90-degree rotation, right? So what if I'm like, okay, rotate it again. Go to your third quadrant now.
Negative X and negative Y.
So yeah, these points here would be, so if I say, hey, rotate this again, it'd be, so again, do your signs. This negative still stays though, right? Now, so now it's both of them are negative. So now this -2 gets brought over to my x. I bring the 4 over, but now this turns negative. Same thing, that -3 gets brought over, and now there's that 4 that gets moved over, but now it's negative. So now every sign there's negative, which makes sense. You can logically apply it. You know, everything in this region here will be negative, no matter what point that is. So now you can just simply plot that. I don't know if this is actually what it is. I'm just doing it for the sake of doing it. So this would be something like that. These are not the accurate positions. I'm just drawing it for the sake of drawing it. And again, I goofed this up. I'm not going to accurately do it. I'm just going to. So rotation is the hardest one for sure. Okay, so let's take a step away from that. Let's take a step away from moving a shape on a grid, and let's look at something called dilation. I'll make this bigger for you guys. If you can't see, let me know, by the way. But so dilations, which is making an object bigger or smaller. Specifically, we adjust by the scale factor. We always go model to original as well. Okay. So what the heck is a scale factor? If you remember, a scale factor, I'm going to put SF for short. So a scale factor is the number by which the side lengths are multiplied to draw the dilation. And again, I will break that down what the heck that means here in a second, if you're not sure. So let's break this down. What the heck does the scale factor actually mean? If I give you a nice rectangle here, and I've just said, hey, this rectangle has a length of 1 and 2, easy numbers for the sake of doing it, right? And I say, hey, the scale factor of this thing is 2. Draw a dilation with a scale factor of 2 as an example question. What does that mean? Well, this is the number that we multiply these side lengths of. So 1 multiplied by 2 turns to 2. 2 multiplied by 2 turns to 4. So what happens is this gets bigger. At each side doubled in length, right? Because it's 2. If this was a 3, each side would triple in length. If it was a 10, each side would, 1 would turn to 10, 2 would turn to 20. But what if I say that, hey, I want you to take the same shape, but I want you to put it a scale factor of 0.5, a half. Is the shape going to get bigger or smaller? Smaller, because you're halving each of these now. So now 1 times a half is, well, a half. 2 times a half is, well, 1. All of a sudden, and these are my new dimensions. So they might ask you to dilate a shape. And when you do that, what I recommend is pick a corner to start from. In this case, I started from the bottom left corner. I recommend that when you're doing a dilation, when drawing a dilation on a graph or chart or coordinate grid, pick an anchor point. Right? So I chose my anchor point as those dots. So if I were to draw all of these in here, it would look something like this. These are my 3 shapes that are in here, for example. I know it's not color coded and stuff, but this is my original. This is my 0.5, and this is obviously my 2. But it's all coming into that same anchor point. Okay, we're almost done. I told you it'd be a lot today. So I'll give you a second. This is it for unit 6. The big thing from unit 6 is the rotations. That's by far the hardest part of it. Okay, so okay, so we'll go into our last unit here, which is unit 7. We'll make this one short, which is also trigonometry. You're like, well, what the heck? We've also done trigonometry before. So here's how this unit differed from the other ones. So our SOHCAHTOA stuff and our Pythagoras, that works quite well, but these only work for right triangles. So, but SOHCAHTOA, Pythagoras, I'm not going to review that over again. That's up in Unit 5 there. You probably will need that stuff for these types of questions sometimes, but more specifically, SOHCAHTOA, Pythagoras, only for right triangles. What we learned this one was the sine law and the cosine law. And these are for non-right triangles. Oops. So that's just the clear distinction here. So again, one of the big things that's important to know is we have so many ways we can attack a triangle. You have to understand what you do and why you're doing it. So we use these for right triangles, we use these for non-right triangles, and we'll learn which one we use and why. So we're going to start out with the sine law. Ooh, too big. So sine law is a general equation. Sine of A. I'll just write it in really quickly actually before I even start saying it. B, C. Sine of A is equal to sine of A divided by A is equal to sine over B divided by C is equal to sine over C divided by C. What the heck does that mean? We'll break it down. Okay, so first, there's a couple key things we need to know. Obviously, the big letters, capitals, are angles. Small ones are sides. So the three facts, we have angles, we have sides, and the sides are opposite of the angles. You can see on this diagram here, I'll highlight it in yellow. The small c, which is this side length here of 10 inches, is opposite of the big C, which is my angle. So just like how we calculated, like how do you find the opposite side? It's opposite of the angle here. Okay, cool. So, you spit out a lot of facts, but when do I use it? We use the sine law to solve for an unknown side or angle when, and I'll show you a trick so you don't have to memorize this. So you can use it to solve for something. You can use it to find an angle or use it to find a side. You use it when you know two sides and the angle opposite one of them, or you use it when you have two angles and the side opposite of one of them. And that's a lot to memorize. So I'll show you a trick.
Okay, so what so one way you can kind of think about it is look at our correspondent pairs. If I look at C's, my two C's, if I draw this like nice little line here, do I have two things there I can use?
Yeah.
Yes. If I'm trying to, so this is an X here. That means I'm trying to find this angle. I'm trying to find the angle of B. If I look at the B side, I can see that I have something I can use over there. So what I have is if I can draw these two lines and I have 3 of 4 things here, right? The second you have 3 or 4 things, you can use those 3 things to find the last part. So I'm using B's and C's here. What I would do is I'd just go to my formula. Don't need that anymore. And I would just fill it in, right? So now instead of sine B, it'd be, well, it'd still be sine B, but instead of B, it'd be 8 inches. Sine C would be 190, sine of 190 degrees. C would be 10 inches, and then you solve. Then you use algebra to solve. So all I now need to do is substitute and solve. So you know this will work. The sine rule will work when you do these little pathways, and I have 3 or 4 things. Perfect, that's sine. So when do I use cosine? So we can use this, and just like before, I'll show you the tip in a second. We use this to find so the cosine law finds, oh my gosh, there. So the cosine law finds the third side length if you know 2 side lengths and the angle between them, or we can use it to find any angle if you know the lengths of 3 sides. Actually, I'm gonna put in a space between these. So there's a couple things here. So first off, when do I use this? This is when I use it, but the really fancy way that we can really say this here as to when do I use this over the sine law is actually, I want to make this black, keep that black. Red. We're almost done. So we use it when the sine law doesn't work. It's as simple as that. You go up here, you circle your things. I can't find 3. The best I can get is 2 out of 4. Sine law won't work. That means you have to use cosine law. You literally use it when the thing you know up above doesn't work. Now, if you remember, though, you have 2 formulas for this. You have 2 formulas for cosine. And the key word here is, what are you trying to find? If I'm trying to find, oh, come on. If I'm trying to find a side length, I'm going to use the one that's a side. Is it the small letters or the big letters that's for a side again?
What was that?
Is it the small letters or the big letters that is a side of a triangle here?
The small ones.
It's the small letters. So I'm trying to find a small letter. So I'm gonna start off with my a squared is this is the formula is equal to b squared plus c squared is equal to 2bc times cos of a. And there's a little visible time symbol here. That's normally not in there, but that's what that means. This is a squared plus b squared sorry, a squared is equal to b squared plus c squared minus 2bc times cos A. There's a lot there, right? But same thing, you fill it in, you solve, fill it in and solve. But I know that this works because I have isolated a side, a little letter by itself. I'm trying to find a side length. Alternatively, if I'm trying to find an angle, I'm going to use the cosine theory that starts with an angle. Cosine of A. Is equal to b squared plus c squared minus a squared divided by 2bc. Square, square, square. So you know that you need to use cosine when sine doesn't work, and you know which of these two you use depending on what you're trying to find, is really what it boils down to. And then so you just substitute and you solve. And you will not need to memorize these. These will be given to you. All three of these formulas will be given to you. I'll show you exactly tomorrow what you will be given. The only thing you're going to really need to memorize from this entire thing is, I think it was these two, but I'll remind you tomorrow. And these things you don't have to memorize, but it's a helpful tool. And then obviously SOHCAHTOA and Pythagoras, that will be something you'll need to have in your memory banks when you go in. But okay, so that's it. So I know that was a crap ton of stuff. So what's happening here is for the rest of the day, what scares you the most? Go to it. One thing I will say though is review four-sided shapes. I think that's unit 5, unit 4. No, yeah, review the shapes, the quadrilaterals in unit 5. I recommend review rotations. It's a helpful thing. And then I recommend try the chapter test for unit 7. Because you want to be able to figure out what you want. I'm confident you guys can solve triangles when you know what you're doing. But the difficult part for most people is identifying what tool do I use. So that's why I recommend try out unit 7's stuff there. So you only got like an hour and a half for this, and then that's it. Then so if you walk out of here and it's like, I don't know how to do four-sided shapes, you will not have that epiphany on Thursday. It just will not happen. So ask for help if you need it. But that's it. So I'll let you guys get cracking at that, but work on whatever it is that you're like, I think I need to work on this, and ask for help if you need it.